All right, let's review some fluids free response for you. So a diver descends on a salvage ship 35 meters below the surface. The ocean density water is 1025 kilograms per meter. Calculate the gauge pressure. What is gauge pressure? That just means like don't include the atmosphere, or all our numbers would be really large. So that's going to be P bottom equals P top plus rho G H. And when we fill that in, we're going to have P top, which is the atmosphere, plus water density is our rho, and gravity, and our height, 35. Now that's going to give us the pressure, but it asks us not to include the atmosphere. That's the definition of gauge pressure, gauge pressure. So P at the bottom minus P atmosphere is just going to give us 3.5 times 10 to the fifth when you multiply all those numbers together. All right, onward. So now it asks for the absolute pressure. So it's like, please go ahead and take that atmosphere and add it back on to tell me about the P at the bottom. So P at the bottom is now going to be gauge pressure plus the atmospheric pressure. So 4.5 times 10 to the fifth pascals, which is also Newton per meter squared. Okay, the diver finds a rectangular aluminum plate and has these dimensions. So 1 meter, 2 meters, and a very thin plate, right? Just a little bit thick. So this is 0.03 meters. A hoisting cable is lowered from the ship and is connected to the plate. The density of this is 2.7 times 10 to the third. And we're going to lift it with some tension, T. Ignore the effects of viscosity. So we're going to lift it up, tension T. What other forces do we have on it? Well, we're going to have some mg, because it's on Earth. And for our forces, we also have the buoyant force up, because we are underwater. So let's calculate on the tension in the cable if it's lifted upward at constant velocity. Okay, so we're going to start with sum of the forces equals ma. There is no a, so all of our forces should be equal and opposite. So we're going to take the tension and we're going to add it to the buoyant force, and that's going to equal mg. So we'll say T plus the buoyant force, which is the weight of water displaced. So rho g v, where this is the weight of water and this is how much is going to displace. So this is actually the volume of the plate, and that is the density times gravity, meaning the weight of water, W of water. And we'll set that equal to mg of the plate. Okay, let's plug in numbers there. Okay, so the sneaky part really on that is just knowing what to write as your buoyant force, right? Weight of water displaced, or because it's not going to be equal to the mg of the plate, right? Now, you're going to ask if the tension in the cable will increase, decrease, or remain the same if it's accelerated upward at 0.05 meters per second. So now you're going to have T plus FB minus mg, that's the sum of your forces, equals ma. And you're going to have on this side the mass and an acceleration upward, 0.05. So instead of these things just equaling mg, now they're going to have to equal an acceleration plus the weight, right? And the buoyant force will just stay the same. So the tension will have to increase. Okay, on to your next one. So we have this pump, and it's going to take water, and it's going to rise it up this pipe and through the house. And the well is 35 meters deep, and you're going to pump it up another 50 meters to the house. We're going to use density of regular water and ignore frictions, turbulence, and viscosity. The residents use 0.3 cubic meters of water a day. This is a volume, right? Volume. Of course, we can turn it into a mass if we want, or a weight, because we know that it's water and we know its density. The day's pumping is completed in 2 hours. What's the work required? Well, work is a force times distance, and you are going to take that energy and you are going to bring it up that hill, mgh, or your work gives your fluid potential energy. So you just have to calculate the mg that's coming up. So instead of m, you're just going to write the density of water times the volume of water. That's m, right? Mass is density times volume. Then we'll multiply by gravity, and then we'll put the heights together. So h1 and h2. Let's write it all out. Work is going to equal 1,000 All right, nice. Now, it asks for the power. This is just classic, right? Power is work over time. You just calculated work, and they give you the time, 2 hours. What they want you to be careful of is that you don't use that, just 2. So go ahead and take your work from above, 2, 9, 0, 1, 2, 3, and divide it by time. But don't use 2 hours. 2 hours times 60 minutes in an hour per hour. And then there's 60 seconds in every minute, right? So we're going to make sure that we convert to seconds. Our power is going to come out as 40 watts. The average pressure the pump actually produces is this number here, newtons per meter, or pascals. Within the well, water flows at 0.5 meters per second, and the pipe has a diameter of 3. At the house, the diameter is smaller. Ooh, I'm sensing a little A1V1 is A2V2. Let's calculate the flow velocity. So it says in the well, that's location 1, we move with a speed of 5, and our pipe has a diameter of 3 centimeters. So we can keep it all in centimeters, that's fine. So we can do pi r squared times V1 equals pi r squared. So that's the area times V2. We can solve for V2. V2 comes out to be 2.8 meters per second, or 2.88, I guess, depending on your rounding. Okay, so just like a heads up there, your units for your radius of centimeters get canceled out over here, one on each side, and so you're left with whatever units this number comes in, this unit will come out in the end. Okay, now let's calculate the pressure at the faucet. It says explain how, but whatever, we'll just do it. So let's take the pressure in the well plus the height of the well, rho g y1, plus 1/2 rho v1 squared, the speed of the water in the well. And let's set that equal to the pressure at the faucet plus rho g y2 plus 1/2 rho speed at the faucet squared. And we know all these numbers because it says the pump is 9.2 times 10 to the 5th, and we can call this next term height of 0, and then we can say here's our flow speed. What's flowing? Water's flowing. And then we have our velocity of the well, which is 0.5 squared. And then we have pressure of the faucet plus 1,000 times 9.8 times our total height, 50 plus 35, plus 1/2 and the water and the speed at the exit, 2.88 squared. Whew! So there you go. You only have one unknown, and you can solve for it. It just says explain how. We don't have